Okay, we're going to start section 11.8, which is called power series. We'll talk about power series for the rest of the way here. Let's see. A power series is a series of the form where you have the summation as n equals 0 to infinity of a sub n is a sequence, times x to the n, which is, okay, if you plug in 0, you got a sub 0 times x to the 0 is 1, plus when you plug in 1, a sub 1 times x, plus a sub 2 times x squared, plus a sub 3 times x cubed, plus etc. A power series centered at C is where you have the summation as n equals 0 to infinity of a sub n, again a sub n is a sequence, times x minus c to the n. Okay, and so in the expanded form there, that would be when n is 0, you got a sub n times x minus c to the 0 is 1, okay, so it'd be a sub 0, plus a sub 1 times x minus c to the first power, plus a sub 2 times x minus c to the second power, plus etc. Okay, now for a power series centered at C, we have the summation as n equals 0 to infinity of a sub n times x minus c to the n. One of the following has to be true. Number one, the series converges only when x is c. Okay, so if x is c, then c minus c is 0. 0 times anything is 0, and so you're adding up 0 infinitely many times, and the grand total there would be 0. Okay. Item 2 says that the series is going to converge for all x values. That's an option. Okay, and then item 3 says that there exists a number r, which is called the radius of convergence, capital R. R is a positive number such that the series converges if the absolute value of x minus c is less than r, and it diverges if the absolute value of x minus c is greater than r. Okay? So let's see. We're going to look at some examples where we're going to find the radius in the interval of convergence. Okay, and that's how most of the problems in section 11.8 are going to go. You're going to find the radius in the interval of convergence for a series. Okay, so in this first example, suppose they have the series, which is given by the sum as n equals 0 to infinity of x to the n. Well, this is a geometric series. Okay, and I know that a geometric series is when the absolute value of r is less than 1, you got a convergent series. And if the absolute value of r is greater than or equal to 1, you got a divergent series. Okay, x is the value of r. So if the absolute value of x is less than 1, that by definition means that x is between 1 and negative 1. So the interval of convergence, meaning that any number that is between negative 1 and 1 is going to make this series a convergent series. Any number that is 1 or bigger, or negative 1 or less, is going to make this series diverge. Okay? The radius is always going to be half of the interval. Okay, so here I've got a radius of 1. Okay? Let's take a look at another example. What if I have the sum as n equals 1 to infinity of n factorial times x to the n? Okay, well, choose x to not be 0, because if x is 0, you're adding up 0 infinitely many times, and the grand total there is 0. Okay, so 0 is going to make this a convergent series if x is 0. Okay, so what if x is not 0? Now, in a lot of these problems, in actually most of the problems, you're going to use the ratio test at some point in the calculation. Okay, that's why, like in section 11.6, I had said that the ratio test is a very important test, and you'll be using that quite a bit here coming up. So let's use the ratio test, and if n is the limit as n approaches infinity of the absolute value of a sub n plus 1 divided by a sub n, that would be equal to the limit as n approaches infinity of a sub n plus 1. Okay, that's n plus 1 factorial times x to the n plus 1. And we're dividing this by a sub n, which is n factorial times x to the n. Okay, n plus 1 factorial divided by n factorial. The n factorial terms would cancel out with part of the n plus 1 factorial terms up top, and that would only leave me with n plus 1 up top. X to the n plus 1, that's the same as x to the n times x, and so these x to the n's will cancel. Okay, I got the absolute value of the whole thing. Now, n is already a positive number. Okay, so n plus 1, I can lose the absolute value bars around that if I want. Now x, I don't know anything about x. So I must keep the absolute value bars around x. Now n is approaching infinity. So I got something that's growing without a bound, n plus 1, and then times some non-negative number. That's always going to be infinity. Okay, so I get infinity there. Now I'm using the ratio test. So what does the ratio test say again? It says if you get a value of the limit that is less than 1, you get a convergent series. Otherwise, if it's bigger than 1, you got a divergent series, or in this case, we're getting infinity. That's divergent. Okay, so and if you're equal to 1, then the test fails. You got to use a different test, right? So any value of x, not 0, but any other number, is going to mean that you'll have a divergent series. So this series is going to converge only when x is 0. Okay, the radius of the radius would be r equals 0, and the interval is just the number 0. Okay, so any other number for x means you got a divergent series. Okay, we're talking about power series. So in the first 6 or 7 sections, we were looking at the different tests for determining convergence, right? And now we're going to look at these tests for a series, but for many possible values of x. So like what are all the numbers x that make this series converge? Well, it's only going to be when x is 0 here. Okay. Let's try another one. So what if I had the summation as n equals 1 to infinity of negative 1 to the n times x minus 2 to the n divided by n? Okay. I'm going to use the ratio test here. Again, a lot of these problems are going to be where you're starting off by using the ratio test. So we have the limit as n approaches infinity of a sub n plus 1 divided by a sub n. A sub n plus 1, that's negative 1 to the n plus 1 times x minus 2 to the n plus 1 divided by n plus 1. And I'm going to multiply that by the reciprocal of a sub n. So if I flip the sequence part, I've got n up top, negative 1 to the n times x minus 2 to the n, that's going to be in the denominator. Okay? And so then from that, now the absolute value of negative 1 to any power is always going to be 1. Right? So it's negative 1 to the n plus 1, and then negative 1 to the n, those are gone. Or another way to look at it is I got negative 1 to the n times negative 1. Negative 1 to the n cancels with this negative 1 to the n down under. So I've got negative 1. Well, the absolute value of negative 1 is 1. N divided by n plus 1, I'm going to go ahead and group those terms together. And x minus 2 to the n plus 1 divided by x minus 2 to the n. So x minus 2 to the n plus 1, that's the same as x minus 2 to the n times x minus 2. Well, x minus 2 to the n cancels with this x minus 2 to the n down under. And that only leaves me with x minus 2 left over up top. Okay, so I got the absolute value of the whole thing. Now, I can go ahead and split up the absolute value bars here because n is already not a negative. Okay, I must keep the absolute value bars around the x minus 2 because I don't know anything about x, right? And now n is approaching infinity. So the limit as n approaches infinity of n divided by n plus 1, that's going to be 1. And x minus 2, that's a constant, right? The limit is in terms of n. So limit of constant is always a constant. So I get x minus 2. The absolute value of x minus 2. Okay. Now, again, I'm using the ratio test. So what does that mean now again? It means that the absolute value of x minus 2, if that's less than 1, you have an absolutely convergent series, and therefore it's convergent regularly. And if the absolute value of x minus 2 is greater than 1, you have a divergent series. Okay? If it's equal to 1, then the test is inconclusive there. You got to find something else. So now I care about when the absolute value of x minus 2 is less than 1. I need to find out for what values of x is this series here convergent. Well, the absolute value of x minus 2 less than 1 means that x minus 2 is between 1 and negative 1. That's by definition when I lose the absolute value bars. So then if I add 2 throughout these three parts, negative 1 plus 2 is 1, x minus 2 plus 2 is x, and 1 plus 2 is 3. So any number, in other words, at this point, any number that is between 1 and 3 is going to make this series converge. Okay, so at this point, like I can know the radius of convergence. The radius is half the interval length. Well, here I've got an interval length of 2. Half of 2 is 1, right? So the radius would be 1. Now, the last thing I got to do is I got to check the endpoints, right? Because I'm using the ratio test here, and it gives me an inconclusive remark when the absolute value of x minus 2 is equal to 1. I still need to know what's going on when x is 1 and when x is 3. Because at those two values, that's when the absolute value of x minus 2 would be equal to 1. So if x is 1, I'm going to go ahead and plug that number back into the series. And I've got negative 1 to the n times negative 1 to the n. Negative 1 minus 2 is negative 1 to the n. That'd be negative 1 to the 2n. Or negative 1 squared is 1. And 1 to any power is 1. I'm dividing that by n. So I have the summation as n equals 1 to infinity of 1 over n is what that simplifies to be. Now that's the harmonic series, which I know diverges. So when I go to write this interval, I'm not going to include 1 in my answer, right? Because I've got a divergent series when x is 1. Now how about when x is 3? When x is 3, again, if I plug that number back into the original series there, 3 minus 2 is 1, and 1 to any power is 1. So I got the summation as n equals 1 to infinity of negative 1 to the n divided by n. Okay, well, that's the alternating harmonic series, which I know converges. Right? We looked at that in section 11.5. And so I'm going to include the right endpoint, 3, and I'm not going to include the left endpoint, 1. So my answer is going to be the interval 1 to 3, where 3 is included. And I've got a radius of 1. Okay, that's how nearly all these problems are going to go here. Okay, so you know whatever the series is, you're going to use the ratio test to start, and then check the endpoints. Be sure to check the endpoints. Okay, I see on some students' papers where they don't do that. That's you know you're losing points then if you don't check the endpoints there. Okay, you're not going to get full credit. So we have to check these two values, when x is 1 and when x is 3, to know if we're keeping them or not. And we're keeping 3. Okay. Let's see. So I'm gonna go ahead and stop the video right here, and we'll take a look at some more examples in the next one there.